Well, welcome. I'm Dr. Jeff Bland, and I'm your host to introduce this extraordinary topic on methylation age, the epigenome, and new assessment tools through evaluating our epigenome. I'm really very, very excited about this program because we're on the frontier of a whole new technology that is going to open up all sorts of new doors for personalizing intervention. This will be a tremendous tool, I believe, both now and more so even in the future for personalized lifestyle medical intervention. So it's with great pleasure that I have two extraordinary experts to really bring this topic to life for you. Ryan Smith, who is the Vice President of Technology for True Diagnostics, a co-partner in the sponsorship of this program, and Dr. Jessica Lasky-Sue, who is a tremendous scientist in this area with a lot of experience, epidemiological and methylation age experience, epigenomics. The two of them are going to bring a lot of news to use to you. And I think at the end of this program, you're going to be one of the few probably in the world that has a really significant understanding of the value and the opportunity that exists through epigenetics and methylation age. So with that as a very ambitious introduction, let me move on and be the kind of the introducer of the topic to you. And so I'll share my screen and we'll have that the topic at hand here. So hold tight, please. So let's see, I want to get this screen maximized. I can here. Here we go. There we go. So advances in the use of the micro analysis of the methylation patterns of the epigenome of immune cells and how this represents a clinical frontier in new assessment opportunities. And remember, it was not too long ago that we were having a lot of individual doubt whether the epigenome could be modified in the adult, whether it was just that in terms of metastability in the fetal development stage in infancy. But now the field has really opened up as many, many studies have demonstrated that the epigenome can be modulated, at least a portion of it, over the course of living through lifestyle environmental factors. This is a tremendous step forward in us understanding how certain conditions are reversible and that we can always get better. And the biology is a two-way street, it's not a one-way street. And yes, our genes are very important establishing our potential, but they don't establish our outcome. It's the epigenetic then signaling at the cell-specific level that then relates to gene expression patterns and how ultimately we perform at the phenotypic level. So these are remarkable changes in thinking, dramatic, almost sea change changes in the plasticity of our biology and the interrelationship that has with how we live, where we live, who we live with, and how our life unfolds. So we're going to be exploring this in some detail over the course of the next couple of hours with you. We'll finish up this program, obviously, with a robust panel discussion among the three of us. So stay tuned. I think you're in for one really great productive ride that will give you a lot of clinical news to use. So with that in mind, let's start down the road. So I'm going to just do a potpourri overview. My responsibility is to tee up the topic with our experts. So I'm going to share with you some of the most recent studies. These are 2023 studies in the main between 22 and 23 that are really demonstrating the vitality of this field and how it's caught fire. It's in a revolutionary stage of evolution. So just to remind you, what we're talking about is taking cells, subjecting them to analysis by looking at what of the genes are methylated using a specific kind of gene chip methylation procedure. And there are two types of cells you can use. There's post-mitotic cells and mitotic cells. If you take cells that are from, say, the buccal cells of your mouth, skin scrapings, those are in general going to be cells that, somatic cells, that are related then to post-translational effects. And so there is a certain value proposition and information can be derived from that. If you take blood samples to analyze, recalling most of the blood that is containing DNA is the nucleated blood cells. Our erythrocytes, our red blood cells, are not nucleated. And so therefore you don't have DNA in erythrocytes. So when you're measuring epigenomic analysis of blood, you're basically measuring in a buffy coat of the blood, which is the Paxil volume of the buffy coat represents our immune cells. So when you do blood analysis, you're principally measuring immunological methylation-related functions that are epigenetically linked to the function of the immune cells. Whereas if you use skin scrapings or buccal cells in the mouth, you're looking at a different kind of cell architecture, cell type with a different pattern. So in the case of many of these studies that we're going to be describing, they've used blood, which then is an immunological assessment. So we're really looking indirectly at immune aging and then correlating it back to these other clinical conditions. So I want to make that a point of differentiation because different cell types, when we examine their methylation, can give different kinds of information. But the majority of these studies that I'm sharing with you are done on blood, which is measuring immune cell type methylation age factors. So here we go. With that as a kind of a background, now what are we looking at clinically? And I think if we were to have asked this question just a few years ago, you recall those of you who have followed Personalized Lifestyle Medicine Institute programs over the last few years, we had Dr. Stephen Horvath present to us about 3 years ago. He's arguably one of the top world experts in epigenomics and epigenetic age calculations and age algorithms. And in his first presentation to us, when he talked about some of these age algorithms, it was still kind of trying to figure out if there was a correlation between methylation age and chronological age and birth dates. And so it was a pretty descriptive way of getting a biology of an immune cell or a somatic cell and tied it to the age and birth dates, chronologic age versus, say, biologic age. Since then, however, there have been many, many clinical variation studies in which correlations are made between a clinical condition and a epigenetic age. So now we're starting to see more clinical utility. And again, Dr. Horvath and many of the investigators that are pioneers in this field have been involved in this crossover translational research now moving into the clinical applications of these technologies. So follow with me now because I'm going to be focusing most on how these transitions go from the early stage assessment of the value proposition of epigenetics as a age determinant into its correlation now with clinical conditions as a condition-specific assessment tool for the status of a person and maybe an early warning sign as to where their physiology will be taking them. Because remember that epigenetics is the upstream regulator of the downstream genetic expression patterns. It regulates the phenotype of cells that ultimately gives rise to the biomarkers and other things that we associate with health or disease. So it's a different way. If you want to really talking about upstream medicine, that's really what we're trying to do with epigenetic analysis. So epigenetic age acceleration in this particular study is really trying to look at how this interrelates with conditions like type 2 diabetes, cardiovascular disease, and other downstream kind of conditions. And we're starting to see a linkage. And I think that linkage then means that we have an assessment tool. It's a prognostic assessment tool. I want to emphasize not diagnostic. We're not diagnosing a condition. We're prognosing a trajectory toward based upon the alteration in the epigenome that would lead to a metabolic state function that could ultimately be called a condition like type 2 diabetes or some form of cardiovascular disease. I think this is a very important point of differentiation to make because we would not call this test a diagnostic test used in this way. We would call it a prognostic evaluative tool, a functional instrument for looking at potential downstream metabolic cellular functional changes that would be associated later with disease. And so you start looking at different age algorithms, and here is where the story gets a little bit more complicated. Now, what do I mean by that? There are literally hundreds of thousands of different sites on our genome that could be methylated. these are generally found around portions of our genome, our genetic structure, that have repeating units of cytosine and guanine, and guanosine. So you have these CPG sites that are repeated, and those are sites that are places, loci, where these methylation marks are located. And so if you want to do a methylation analysis of your genome, you would like to see all the places where these CPG sites become methylated. Now, what you don't know at that point is which of those CPG sites have clinical importance and which are just there for the ride. I'm saying this a little bit exaggerated to make a point. Some of those will be much more functional in determining outcome metabolically than others. And so the studies now that are ongoing and refining and iteratively improving our analysis are the studies are trying to define what of the literally hundreds of thousands of CPG sites are the ones that do the heavy lifting, are the ones that are most important. So that leads to then a series of algorithms that are mathematical models using different collections of these CPG sites to see how they correlate with chronologic age or other types of biological parameters. Could be immune cell it could be inflammatory function. It could be virtually any biological principle could have a correlation in between these epigenetic methylation sites. So these particular algorithms are developed by different investigators in the field. They have different names, and they have different correlation coefficients in with different indicators of physiological function. So we might do one methylation analysis at the laboratory level, but we may do many different types of informatic analyses using these different age algorithms, these different informatic approaches. So we have Grim age, we got pheno-age, we've got, as you can see from this chart, a variety of different ways of assessing the data that comes from our methylation patterns of our genome using different kinds of collections of these CPG methylation sites and different ways of interpolating their relationship to clinical things like white blood cell counts like monocyte or CT4 counts, or various types of biochemical parameters like HSCRP or serum glucose or BMI. So these correlative algorithms allow us to dissect and interrogate what are the best ways of using this methylation data for a clinical outcome. And so you can see there's a range of different correlations for the different types of things that we might want to know. And using the right algorithm for the right question to get the right answer is part of the story. I hope that made some sense. So let's look at BMI, body mass index, connection to these algorithms. So if we were to look at pheno-age, which is one of the algorithms, you'll see that pheno-age correlates very, very closely with a high correlation coefficient with BMI, particularly in males. And you'll see that there's a very, very distinctive, as your pheno-age, your methylation age measured by that algorithm called the pheno-age algorithm, connects very closely with your body mass index. With people with a low pheno-age, meaning young, immune cells have a low BMI, meaning lean, and those people that have high pheno-age, meaning high methylation and higher immune cell age, have a correlation with high BMI. Now that probably makes some sense, doesn't it, from a clinical perspective, because we know that obesity is associated with angry fat often, which is an inflammatory state, so-called inflammaging, and that is associated with increased risk to age-related diseases and correlates then with this higher pheno-age. The methylation age is determined by the methylation patterns of the immune cells, which means in part that aging of the immune system correlates itself with increasing body mass index in an inflammatory state. So another really important kind of interrogation tool that we see that's associated with a metabolic outcome. So what happens then if you put a person on a long-term calorie-restricted diet? Does that influence then their pheno age or their, let's call it their methylation age, their immune cell age? This is a trial that's recently been published called the Calorie Trial done in Europe. It's a really interesting controlled trial of modest calorie restriction, looking at the outcome and measuring then using various algorithms the influence on methylation age, immune age. In this case, one of the algorithms that was used was the Dunedin-Pace algorithm that was, I think, a very, very well-respected algorithm for looking at immune cell relationships to metabolic age, and showed that calorie restriction, modest calorie restriction in humans, was capable of lowering the age as measured by the methylation study, the Dunedin-Pace algorithm, which again shows that we start seeing biology connected to methylation age in the methylome. A very, very, I think, major breakthrough in our clinical utility of understanding of the clinical utility of the methylation assessment of in this case, immune cell age. So taking this a step farther, now we're getting a little bit more esoteric. What about grip strength? Now, that might seem to you like you're not going to tell me that grip strength is connected to methylation age, are you, Jeff? And the answer is yes, it is. And it's not just one study, but there's actually several studies that have demonstrated this. This is a recent 2023 study looking at grip strength being inversely associated with DNA methylation age. Now, why might that be? Again, we have to continue to ask the question of how this mechanism ties to anything clinically that we know. Well, we recognize that grip strength is a surrogate marker for function of the energy processing mechanical aspects of musculoskeletal function. And that is in part related then to the things that drive musculoskeletal function, which and drive energy within that system, which is mitochondrial oxidative phosphorylation. So this would suggest that there is some type of a correlation between bioenergetics as seen through muscular strength as measured by grip strength, bilateral grip strength, and your DNA age of your immune system. So again, a really powerful kind of sense that what's going on at the epigenomic level that's associated with the way we're living, what we're exposed to, how we're eating, our stress patterns, our sleep patterns, our exercise patterns, are implicating different methylation patterns of our genome, which translates phenotypically into things like metabolic function that associates itself with grip strength. So it's, again, showing you the portfolio of different potential clinical applications that come from this association, and why this is, I think, going to be such a valuable prognostic evaluative tool, using these different algorithms for evaluating methylation association to function. Well, what about correlation of methylation pheno age to dietary factors that associate themselves with things that we associate with diabetes or pro-inflammatory states? So here's a really interesting, again, 2023 study looking at the association between accelerated pheno age. Again, remember, this is just one of the algorithms that you use to process the information from a methylation analysis of the genome, the epigenome. There is a very strong correlation then between the pheno age and between inflammatory dietary components. So a inflammation prone diet connects itself to increased pheno age. Now, the power of this is that this is modifiable. So as we saw from the calorie study, intervention then can lower your pheno age. And so this is where the real secret sauce comes from these tests, because it allows us to kind of assess what is the outcome, the advantage that's come from intervening, and how do we measure it in terms of a functional level? The surrogate marker methylation age may be one of the most powerful tools we have for assessing that transition. It's not looking at the downstream pathology, it's looking at the upstream regulation of gene expression patterns and how they ultimately translate into things like inflammatory burden or altered glucose tolerance or altered lipid patterns. So I think that these are really a whole different family of information gathering algorithms that give us different kinds of insight into all the direction, the trajectory that a person is going as it relates to these functional outcomes. This is so well suited for personalized lifestyle intervention because it's not just looking at the disease outcome of a specific biomarker, it's actually looking at the impact that a complex personalized lifestyle intervention program can have on functional states of gene expression. Well, let's use stress as an example. You remember Bruce McEwen, unfortunately now deceased recently, passed away at 80 years of age, but he was the father of allostasis and the whole concept of allostatic load, and published literally hundreds of papers across the, I would call it the immunometabolism area and its relationship to stress. And so the question is, how does stress influence the metabolome? And can you use methylation patterns of the genome of the immune system to actually understand some of the effects that stress is having in terms of inflammatory burden? So that's this particular study, again, a 2023 study, very powerful, detailed research, looking at the influence that allostatic load, the stress load, has on accelerated methylation-related aging of the immune system. And this is tying it back, as we talked about earlier, to alteration in energy-producing processes of cells, the mitochondrial oxidative phosphorylation connection. So now we're saying, whoa, just a minute, you mean that this methylation age has some connection to mitochondrial function and to how stress could influence that? And the answer is yes. We're starting to emerge a very, very interesting new way of thinking about the assessment prognostically of the trajectory towards these disturbed metabolic states of immunometabolism that translate into this whole array of clinical phenotypes that we see associated with chronic illness. So when we look at the epigenetic aging in this study with varying allostatic load, we see that the increasing allostatic load is associated with increasing biological age by all clocks, but particularly sensitive to the pheno-age clock, where you see a very, very strong correlation. So again, there's all of the age clocks that are used show a trend, but the pheno-age appears to be the most sensitive of those that were studied in picking up the allostatic load connection to biological aging, in this case, immune aging. So, you know, this in the paper was summarized in this little cartoon, this little diagram. And I think this is very powerful as a visual because it helps us to understand much better the kind of difference between an assessment tool, a biomarker for a disease, versus a prognostic assessment tool for a functional change in the cell, how it functions in regulating gene expression. So you'll notice they're talking about the signal is allostatic load, stress-related load, that then modulates then the methylation patterns of the genome. That methylation pattern of the genome changes the gene expression patterns, which then do what? Alter the kind of molecules that are produced from the genes into this inflammaging architecture. So we start getting different molecules produced by cells as a consequence of this change in their epigenomic pattern, particularly related in this case, as I said, to the immune system because the cells that are used in this study were blood-derived white blood cells. So again, we can take this to many different other applications. There's where the literature is going. Again, I'm trying to emphasize these are all 2023 citations. Associations between cardiorespiratory fitness and lifestyle relationships with DNA methylation. This is a a recent clinical study in humans, the Wasita study, and again showed very, very positive correlations between lifestyle, what we call healthy lifestyle interventions, improved cardiovascular and cardiorespiratory fitness, and reduced immune age, biological age, using the methylation patterns. So again, showing the range of different applications that this assessment method has. When you actually, again, go to the data set, the gene block data set with different informatic tools used, you'll notice that some of them are more correlated with certain principles than others. This is just, again, an example as to why when you have your data, your methylation data, you probably want to pass it through a number of different algorithms that are really related to different sensitivities of the phenotype. There's not just one algorithm that covers with high specificity all clinical outcomes. So it's the right data against the right lab test against the right clinical outcome you're looking for. And I think that's where really good laboratory work is done, is not just in the analysis itself, but also in the interpretation of the data and signaling to the clinician what are they really wanting to know, and making sure we use the right informatic test algorithm to evaluate that outcome. We also see the same thing happening in osteoarthritis. There's work now ongoing with articular chondrocytes and their epigenetic alteration through lifestyle principles, exercise patterns, trauma, nutrition. So this, again, I'm just trying to illustrate that this tool can be applied across so many different potential clinical needs. And I already mentioned the connection to mitochondrial function, but this is just another of the papers that really talks about OXPHOS alterations and its relationship to alteration in methylation patterns and the age accumulation within immune cells as a consequence of conditions that alter mitochondrial function. This particular paper was done in the extreme case of actual inborn errors of mitochondrial function, the so-called mitochondrial disorders, mitochondrial diseases. Once again, in that kind of extreme case, showing significant epigenetic methylation changes in individuals that carry the genetic problems with regard to mitochondrial function. Remember, mitochondria has its own DNA, and that DNA can, although it's small in amount compared to nuclear DNA, it can also be methylated, and it also can be altered in its functional state. So that gives rise to even inborn errors of metabolism that are associated with mitochondrial DNA defects may be modulated into the phenotype by their methylation patterns epigenetically. So that gives flexibility for intervention even in those that are carrying certain genetic inborn errors. To what extent that can be modified, it's probably not as great as if they didn't have that genetic aberration, but it does give a range of dynamic variability based upon how you pattern the epigenome of mitochondrial DNA. So this is actually looking at the data in some greater detail. And what I really just want you to understand, because this is really just a kind of a shock functional diagram, unless you dig deep into the data, is that you can see this mitochondrial alteration is associated with the conserved epigenetic remodeling. And that based upon these clock mechanisms that we've been measuring or we've been discussing, you can see variations then in what we would consider mitochondrial age associated with the cell functions that are having their epigenome evaluated. So I think this is, again, a really important advancing understanding of the power, the value of methylation, age, and the epigenetic evaluation of genes that have become methylated within this family that are associated with functional changes in the phenotype. So this diagram talks about a model that includes the epigenomic evaluation into the assessment of function, and how that can lead us into understanding not only the state that the person is in, but also to tracking the performance they may have and the outcome as it relates to therapy and intervention. So healthy lifestyle, DNA methylation patterns, age acceleration, this work is coming on rapidly, and I think it represents the cutting edge of this whole field. It's so fascinating for me. I recall the first education program that we did on epigenomics and nutrigenomics was about 12 years ago, and we were just in the infancy of understanding how it wasn't just kind of selective polynucleotides, the SNPs, that regulated how the individual performed, but it was also the epigenomics of how the genes were marked that then related to their function. We did not have the tools back then when I started talking about this 12 years ago to actually do an epigenetic analysis. Now we have these functional tools that allows us to tie together genomics with epigenomics in such a way that we can look at how nutrition, lifestyle, exercise, stress, toxins, all influenced in the outcome that we call the cell biology, that is the function of our tissues, organs, organ systems in our body. So this is building up an architecture of prognostic assessment that gives us potential insight that we never had access to until recently. It's very, very exciting. And so the methylation-based biological age is, as I said, associated with so many different clinical conditions. Now, this is a series of papers that have been published recently on the connection to hypertension. And now we ask the question, starting to get more detailed and deep drilling into this. Okay, what are the specific loci of the epigenomes, the CPG sites that I said are hundreds of thousands of them within a cell? Which are the ones that are the most important, and how do they control the function that translates into things like hypertension or dysglycemia or inflammaging? That's where we're going next, is to actually understand better what are the islands within our epigenome that have the greatest functional important relationship. So now we're kind of on the broad brush stage. We're I say, working in maybe a little bit of the smoke. We haven't come out of the smoke into the clarity yet. But even with that level of uncertainty, we're able to start making some very important clinical understandings about the prognosis of the individual and how intervention, personalized lifestyle intervention, can influence then the outcome of gene expression. So that takes us then into the extraordinary work that Dr. Kara Fitzgerald has been doing. This is the second of her studies recently. This one was recently published in small clinical observational trial in women, looking at the effect of a methylation-supported diet and lifestyle on biological age-related functions using these age clock determinations, and showing clinically significant reduction in number of age of years from 55.83 down to 51.23. So this is after an 8-week or a 2-month intervention with diet and lifestyle. So again, these are all building the support for the fact that these are reversible, that methylation age is a useful assessment tool, and it tracks and ties to ultimately the phenotype of health, and in the end could even tie to the phenotype, obviously, of disease. But I think for us in the personalized lifestyle medicine camp, what we're really interested in is the sensitivity that these tests have in tracking performance at the genomic level of our intervention, so that we're not going to get into the disease state. We're going to be able to have the opposite part of the street, the reversal, the rejuvenation part of the curve being realized. So this whole concept of immune rejuvenation becomes an important, kind of objective, utilizing our intervention and this tool to measure the outcome. So in summary, just setting the teeing up for our experts that are going to tell you much more about the test, how it's used, what its strengths and limitations are. Let me just summarize by saying the age-associated epigenetic change also relates to things like sperm. And I think this is very, very interesting. If you look at the number of reproductive problems we're having right now, which are related to alterations in both the patency and I guess it's a functional response of both the egg and the sperm in reproductive medicine, that we're starting to see more and more low sperm counts of sperm that's not motile. It doesn't have the right metabolic power. It's mitochondrial can't generate the energy necessary for the sperm to swim effectively and impregnate the egg. And so we're seeing more and more IVF and artificial means of reproduction. And it's kind of scary because the most recent data that's just been published in 2023 suggested that the rate of decrease of sperm count in males, that if it were to continue for the next 15 to 20 years, we may have a situation where virtually all pregnancies start by in vitro fertilization. That would be scary on many levels, but it's certainly indicative of lots of things. Without getting too far deeply into this, what we do know, however, is you can measure sperm methylation, and that is correlated with sperm aging, just like cell aging in general. So there may be many, many different ways of utilizing the methylome and its relationship to cellular function, even this transgenerational inheritance, because if the sperm contains certain epigenomic patterns that can be translated on to the next generation, it also leads us into understanding what kind of conditions we see prevalence of that may come from epigenomic changes from our environment and lifestyle. And certainly we look at things like autism, we look at things like asthma. There are a whole variety of conditions that seem to be rising in prevalence much faster than we would expect that may be tied to these epigenetic changes. So it's the front edge of a new revolution. We're excited at PLMI to be part of it, and we're very pleased to have True Diagnostics as our partner as we start to really explore the clinical power of methylation aids. So with that as an intro, let me move now into our clinical experts that will give you much more news to use, and then we will finish up with our panel discussion that I think you'll really enjoy vicariously participating with us in that discussion. So stay tuned, and so I'll get out of the screen here and stop my share. And thank you all very much for tolerating me and this introduction, long-winded introduction. But I think now we're ready to move into the detailed information supporting this new technology. See you at the question and answer and panel discussion later.
Everyone, my name is Ryan Smith with True Diagnostic, and today I'm excited to give an introduction to this Omic age algorithm and the really amazing lecturer we'll have next, Dr. Jessica Lasky-Sue. My company, True Diagnostic, has really worked with Dr. Lasky-Sue over the past really 3.5 years now to create this new biological age algorithm. So what I'd like to do today is just introduce you to the topic so that Dr. Lasky-Sue can do the rest and tell you why this is such an amazing product. So to get started, I want to go a little bit into the history of biological age clocks. You might have heard about these a lot over the past few years as people are using them left and right to really quantify the biggest risk factor for all chronic disease and death, which is this aging process. And so this has really started in 2013, but it's come a long way in this last 10 years. Really, I would liken epigenetics as a class of development to the same way that genetics was growing in the past 25 years. It's really exploding at the moment and will be a must-use clinical tool in the next few years. But this really started in 2013 at UCLA with Dr. Steve Horvath, who used DNA methylation to look at chronological age and actually create an algorithm to predict chronological age. And at first, this wasn't meant to be a health tool. It really was used to date people like refugees to see if they were adults or minors and therefore eligible for asylum, or to even test DNA at a crime scene to see how old a suspect might be. But when they looked at really large cohorts, like the Framingham Heart Study, for instance, they started to notice an interesting trend, which is that those people who were older than their chronological age at this testing tended to have worse healthcare outcomes, meaning that they were having more disease and earlier rates of death. And on the converse side, those people who were younger with this testing than their chronological age were protected against those negative outcomes. So even though this was meant to be a process to calculate chronological age, what it ended up being was a way that was measuring this biological aging process. So we could call clocks that are trained to predict chronological age first-generation clocks, or as you can see here on the left, there are a multitude of these. The problem with these clocks, though, is that the better that they get, the closer they get to just telling us your birthday, which for most people is something we don't need. So really in 2018, 2019, the development started to improve. And these started to be called second generation clocks. And these clocks were really set up to tell us a little bit more, capture the biology of aging rather than just capturing the biology associated with chronological age. So these algorithms were trained to predict things like 9 blood-based biomarkers in the blood, or to predict the time until death to see if we could predict death accurately, or even other hallmarks of aging like telomere length. And these clocks were better than those first generation clocks. And the reason we know is because if we had 1 year of age acceleration in each clock, the rates of disease we would see with the second generation clocks were much, much higher, showing us that age acceleration is more predictive of those negative disease outcomes we associate with aging. And so this was a big step forward. We even had another development, which is in 2021, the publication from Duke and researchers at Columbia was the Dunedin Pace. And this is the first ever third generation clock. And this one actually looked at 21 blood-based biomarkers, or not even just blood-based, but other health biomarkers. So things like CRP, your total cholesterol, your lung functioning measurements, like your FEV1, or even your HbA1c, and even gum health measurements, and turn this into a biological aging calculator across time, where we actually followed the same people from the moment they were born all the way until their age of 51 to tell us how fast someone's aging right at this moment. This is the first time that a biological age clock had been done longitudinally in the same patients over time instead of multiple patients across multiple different age groups. And that represents the first ever third generation clock. And this clock, again, was much, much more predictive of outcomes and even showed a wide variety of associations to faster aging being linked to things like cognitive dysfunction and IQ decreases, reduced grip strength and muscle mass, and even increased facial aging. And so over the years, we've gotten better at actually measuring the aging process as it relates to the biology that you might experience as you age. And these clocks have gotten better because of it. But if we look at the best clocks, the clocks that perform the best, they're the ones that actually capture the most biological information. So GrimAge is a good example where they actually use DNA methylation to predict several different plasma proteins like leptin or cystatin C, or in the case of that Dunedin Pace, the only third generation algorithm, we're quantifying age in a better way by looking at over 21 different blood-based biomarkers. And so these have been the best in terms of predicting outcomes of aging and have been some of the best ways to classify age. But if we want to do even better than this, we have to get even more complex. And that's because aging is incredibly complex. Here you can see that when we started this company in 2020, there were only 9 hallmarks of aging. Now there's recognized 14 or 15 different hallmarks of aging. And so aging is incredibly complex, and how we define this needs to get better over time. So that's what I'm introducing today, this Omic age algorithm, where we actually took a multi-omic approach. And this is really following the central dogma of biochemistry, this idea that genetics is our baseline starting feature. Then we have gene expression, what genes are turned on or turned off. And with that, we look at epigenetics. So things like what we're measuring with DNA methylation. From DNA methylation, we go to what is actually transcribed into mRNA or RNA, which then codes for proteins or peptides in the body, which we call proteomics. That leads to metabolomics, the metabolites of processes in the body, and ultimately the phenomics, or what actually is happening. That could be as simple as if someone has blonde or brunette hair, or if someone has diabetes or not diabetes. And so we really, to capture aging, had to look at this entire process. This is why it took us 3 years. We created one of the most robust data sets of all time. But what we were able to do was create Omic Age, the algorithm Dr. Sue will talk about. And I just want to talk about why this is important for you as a clinician if you're interested in measuring biological aging. One of the first reasons that these clocks are better than all previous clocks in a lot of different areas. One is precision. In previous clocks, like the Horvath 2013 clock, if you tested the exact same sample, you could get variations in age of over 4.9 years. And that really is not effective, because if you really want to measure true biological change, you can't have such swings in the measure. Now with our Omic Age, we have less than a 0.2% variation on testing the same sample. So it's incredibly, incredibly precise. One of the other big issues is that in measuring blood, we're measuring multiple different types of cells, and every cell has a different epigenetic expression. This can lead to some really tough problems when we're trying to quantify age. So for instance, even if we took an individual's T cells, we looked at their CD4 and their CD8 T cells, we could get up to 20 years of difference in the same blood sample from just different types of cells. And so in order to control for this, we've been able to do this in this new algorithm to make sure that if someone is sick or has an autoimmune disease, we're not reading out incorrect biological ages. We're controlling for changes in immune cell subset. That's been a huge, huge benefit to this algorithm, which will reduce variation as you're testing your patients and making sure that you're getting a real and true biological age rating. One of the other really amazing things about this algorithm is we can actually connect it to your patient's increased or decreased risk of multiple diseases. So we can actually tell you how your aging is going to increase your relative risk of cancer or death or type 2 diabetes, for instance, and multiple other considerations. So we can actually tie this to all of these other diseases. The other thing is that this algorithm is much, much, much better at being consistent with the other clinical pictures you're seeing. For instance, some of these early algorithms, you could have someone who looks very unhealthy by all other metrics, is not doing well, but then they have an amazing biological age. And that doesn't make a lot of sense. But with these newer algorithms, everything makes a lot of sense. And the clinical picture and the aging picture will match probably what your expectations are for a majority of the time, although there are going to be some outliers to that. Another good example of this is that those first generation clocks don't always respond to intervention like we would anticipate. Caloric restriction is a good example. Caloric restriction is one of the most well-validated interventions for health span and lifespan improvements. But when we tested this in humans, we actually saw that those first generation clocks actually go up with caloric restriction, which doesn't make a lot of sense. Whereas those third generation clocks, like the Diagnostics pace, go down. And so that's the reason that those first generation clocks, the ones that are trained to predict chronological age, are really not effective, and why they shouldn't be used clinically. And really, we should mention that we're the only company that offers any published algorithms that are second or third generation and really no longer do any first generation clocks. And it's for this reason, so that we can see change in the right direction and have that be reliable to outcomes. And speaking of reliability to outcomes, our new Omic age outpredicts every other previous clock in almost every disease category. In particular, we have over a 90% accurate prediction of survival in the next 10 years. We can tell you if you're likely to die, and we're accurate 90% of the time, compared to chronological age, for instance, which is only right about 75% of the time. So that's a significant improvement. But not to, I think the most important improvement here, and what we'll talk about later today with Dr. Su's talk, is the why. Previously, we've been able to tell if you're aging faster or slower, but we haven't been able to tell you what's probably driving that. Now we have the resolution to maybe postulate ways that you might be driving your aging process. And that's because we actually use DNA methylation to tell us about other clinical, metabolite, and proteomic factors, which might be increasing your score or decreasing your score. And so we do this by these, what we call these epigenetic biomarker proxies, where we can actually tell you through DNA methylation, things like your HbA1c, your creatinine, your glucose, or triglycerides. We can actually tell you how it's impacting and what degree it's impacting your biological age calculation. And so this is what our report would look like, where it could actually quantify that level for you and tell you where you're at in the population. But on the right, you can see that we can also show you the things that are negatively or positively improving your score and the relative strength at which they're improving or decreasing your score. And so now we can really add a lot of resolution to the why to create personalized treatments to really turn back that clock. And when we look at big cohort analysis of this is all the different 36 features we read out. We can actually see their connections to disease. So for instance, in this particular example, you can see that our predictions of HbA1c and glucose are highly related to things like type 2 diabetes, which makes a lot of sense considering we know that those classical blood-based biomarkers have the same associations. But we also see this with lesser known associations that mimic what we know in the literature. Here's a good example with insulin-like growth factor binding protein 2, which we know is very highly correlated to weight and BMI and obesity. And here we see a sort of a negative association for those who are obese, meaning that protein goes down, where in underweight, that actually tends to go up. And this backs up what we know already. So these epigenetic biomarker proxies are able to quantify these other values, but also can be used in these really complex models to tell us why or why not we might be aging. But they also provide us for interventions. A good example here is in some of our metabolomic scores, where we're able to quantify things like uridine or ribitol or vanilla acetate, which have I would say, information about what processes might be affected within our body. So one of these is uridine. Uridine is positively weighted in our algorithm, meaning that the higher the levels of uridine, generally the better your biological aging. And when we look at uridine, we can actually see that this makes sense. It has several different studies on aging, not only intestinal aging, as you can see here, but overall lifespan. And it even has been shown as a metabolite, which really helps in regenerative processes, even in other animal species, like as salamanders regrow their tails. And so uridine has been identified by our algorithm as an important product, and we've shown that supplementation can also improve this. We also know that one of the other metabolites selected was carotene-diol. This is a carotenoid which is found in spinach, kale, and yellow carrots. And we've shown that higher levels of this also represent better biological aging. And this backs up, again, other pieces of information we've seen before, which shows that even in previous algorithms, the higher carotene intake, the better your biological aging. And so, again, this backs up not only previous assumptions and things we've already known about the aging process, but has identified unique factors like uridine, which previously haven't been described and might be used for treatments. And so together, I think the bigger idea here is that this is the best way to quantify biological age, and Dr. Lasky-Sue will really go into that. But as a platform, DNA methylation is really exciting, and we can actually quantify DNA methylation risk scores, like polygenic risk scores you might get from a DNA analysis, but generally these are much, much better. In this study from a UCLA researchers, they found that methylation risk scores improved 139, prediction of 139 different outcomes, whereas polygenic risk scores only improved 22. And so this shows that as a concept, methylation risk scores can even go above and beyond what we know about genetics. But in addition to that, we know that those surrogate biomarkers, those epigenetic biomarker proxies of the EBPs we're talking about, can also improve resolution. A good example here is GrimAge, which had at first 8 plasma proteins, expanded that to include HbA1c and C-reactive protein, and was better able to predict disease. So I think that this shows how methylation risk scores and these epigenetic biomarker proxies can be used to consolidate many, many different labs all into one, and then also improve our prediction of some of these really complex outcomes like aging and death. So with that, I'll give it to Dr. Lasky-Sue. Look forward to answering any questions in our forum later today.
I'm really excited to be talking about this project tonight because this has been a gigantic effort by so many people at True Diagnostic and my lab at Harvard Medical School. And I've entitled this talk, Precision Aging, using Omics and EMR to optimize aging for each individual. And I want us to be thinking about this idea of precision aging as we are going through this presentation. And I know we have a range of people on the call, so I'm going to start from the beginning and move on to more complex things. But to just get us all on the same page, I want us to step back and ask the question, how do we think about aging? And of course, there's the idea of absolute aging, which is just an issue of time, right, and chronological age. And when we look at that issue of time, there are some people who we may look at and they may seem timeless, where time stops, right? And they seem like they look the same over 30 years, like we see here with Jennifer Aniston. And in thinking about that, while we just looked at that visually, we know that biologically, while we may all have an absolute chronological age, there is tremendous variability in what actually our biology is doing and how fast we are aging and why that is. And so that's just highlighting this idea of the difference between chronological age and biological age, and recognizing that those two are most often not the same. And in thinking of it here and in looking at these two individuals, we can think about the idea of difference is in chronological age and biological age on the spectrum. Well, while we are always increasing chronologically in terms of aging, biologically, we may not even always be increasing. Sometimes we may be decreasing, but there is a variability around what our chronological age is in terms of what we are observing in terms of biological age. And of course, that's due to a lot of mechanisms biologically. And we know that there are a lot of ways that we have in our own selves the power to increase or decrease our biological age by the choices we make. Yeah, some of the choices we make, some of this variability may actually not be us. It may be underlying genetics. But can we understand biological age? And actually, can we measure it? And a lot of what True Diagnostic and their mission is to measure it through biological aging clocks, and actually the first in class best biological aging clocks. So as we think about biological aging, and as we can recognize there, I have the two people from the figure before put here, and the woman who is very fit, who's actually in her 60s, is actually a real Instagram star. You can see certainly that while people may be increasing at the same chronological age, certainly biological age does vary. But I want to step back and also highlight this concept of biological aging and what we as researchers think of it. And I want to really highlight this point that there has been a paradigm shift in how we as researchers think of aging. And fundamentally, we think of it as a global crisis in itself. We think of it as a disease, right? That we think of aging like we do any other chronic disease outcome that progresses with time. And that in fact, in many ways, we may be able to reverse biological aging and perhaps even prevent it as well. And so when we think of it in that framework of a chronic disease outcome, and that it is slowly over time, you may increase, but there is leeway and ability to prevent it to some degree. We want to think about why that is so important. And it's simply put, because if you think of aging in that framework, it is absolutely the biggest risk factor we have for any chronic disease. So this is like the master of all masters chronic diseases. And we can understand that and recognize that by just realizing that if we think of it this way, it is by far the biggest global health burden. And in fact, if we can just reduce this a little bit, we can have tremendous impact on public health. And here's some statistics. If we delay aging by 7 years, we cut disease incidence in half. And not only that, if we slow aging by just 20%, the US alone would save $3 trillion in spending over the next 50 years. So tremendous impact on public health. And so fundamentally, I myself, when I think of aging, I think of aging and biological aging as really this big, broad conceptual concept of the totality of health of an individual. And how can we understand aging in that broad framework? And what utility can it have? And while we think of it as the totality of health, I want us also to recognize that while we have a very large impact on our health, it is not just us. There's always this concept of nature versus nurture, right? And what can you do? And what are just the genes you were born with? And I will illustrate that with this example actually from my family. Here is my great-grandfather in the middle here. He was born in 1894. He lived to be 107. And by golly, if he actually did things well, like took care of himself, I don't know how long the man would have lived. But this man was diagnosed with black lung when he was under 30. He chewed tobacco until the day he died. Yet he never developed any type of cancer. He never developed heart disease. And at the end of his life, he ended up dying of pneumonia, and was running around while this happened. So certainly, this is an example of nature. There was not much nurture going on here, but nature was in his wheelhouse, and I hope I inherited those genes. So with that in mind, my point is, when we think of aging, we not only want to think about important concepts of biological aging, but we also want to think of precision aging. And what do I mean when I say precision aging? Well, for those of you who are MDs and have looked in research, right, the concept of precision medicine and personalized medicine now is really big, right? What can we do to treat our patients to optimize their health. And I want to just spin that paradigm around to aging. As researchers in aging, we can ask the question, what can we do to optimize an individual's aging? And how can we optimize it differently for one individual versus another? And in thinking about that, we can start off with a big question of, well, number one, we need to get some estimate of their biological age. And once we get that, we need to actually understand for that individual, what is driving their biological age, because it may be different for George than it is for John. And once we identify that, can we identify the mechanisms by which that is operating, and perhaps then utilize that information to optimize and or prevent disease? And again, this is on an individual scale. So in thinking about precision aging, I also want to think about the context of which, as clinicians, precision aging is important. And of course, this is a context of thinking of this with how clinicians work every day. And what is that they use? They use the electronic medical records. But as someone who does health research and in aging research, my vision of an EMR is not really what it is today, but the potential of what it can become. And while I know there are a lot of barriers to that, and we could have a lot of conversations about that, my vision of what the EMR should be is where John Doe clicks on his personal health profile and out pops an estimate of their biological age, but then personalized estimates of their disease risk, their potential response to different drugs, information about genetics, underlying genetic predispositions, other exposures they may have, things like gut health. But then most importantly, this idea of disease prevention, and that goes into all of these ways that each individual may be able to modify their disease and or aging profile to be as young as it can. And my point in showing this is that this paradigm shift of personalized medicine is exactly what precision aging is about. It's about making this a reality. And so how can we think of this now in the context of what we're talking about today? And we've talked about, there's a great opening by Varun about ideas of the aging clocks. And I want to talk about aging clocks in the context of precision aging and why what we did today is so much different than what has been done, and how we have just started what is now an explosive area of research and ways that we can add on to this to give translational potential for the patient and for the individual who wants to optimize their health. And I'm going to be talking about this in 3 different areas. The idea of creating a biological aging phenotype, and how we can predict that biological aging phenotype, and how we can understand the biological aging phenotype. Now, let's start with creating. And with each one of these areas also comes a specific framework and focus that we're going to talk about. So in the idea of creating a biological aging phenotype, I want to talk about creating a biological aging phenotype in the context of the EMR. And why is that? Well, for people who want to potentially implement something, fundamentally, if we can use data that are available in the EMR, that is incredibly important, because potentially we can recapitulate this. And that is a very important framework for which to have. So for this first step, I want to talk about creating a clinically relevant and reproducible biological aging phenotype. And I put in here clinically relevant for many reasons, as we'll discuss. And in what Varun opened up with, he opened up with a brief outline of the first generation, second generation, and third generation aging clocks. And those aging clocks, the second generation and the third generation, are based on aging phenotypes. And I'll highlight a few here because these are ones that are very popular and have been, I think PhenoAge is the first one I want to highlight, which is really one of the first second generation aging phenotypes that gained a lot of attention. And what was the basis of PhenoAge? Well, a lot of PhenoAge was based on clinical data, diagnoses, and labs. And as you can see, all of those things are important to aging. And all of those things are important to aging well. And that is something we also want to talk about. It's not just about aging, it's about aging with wellness. Now, another very popular and a very powerful aging phenotype that came out or approach was simply this idea of estimating time till death. And GrimAge is a phenotype where we can estimate time till death. And that fundamentally is also important too, because we don't want to die. So I want us to think about both of these concepts, the concepts of mortality and the concept of wellness. And I want to just highlight, as Varun shouted out to, also what we aren't going to be talking about today, but certainly is an area we are going to be getting into more with EMR data, is the rate of aging. But while there have been clocks based on the time till death, and there's been clocks based on a lot of clinical labs and phenotypes, I want to posit that for the best overall characteristic of what we want, it is not one or the other. We want to live well in wellness, and we want to prolong death. So one of the questions we asked to begin with is, can we create a phenotypic clock that uniquely combines these two things? Not only can we combine these two important aspects of aging, but can we do it in the framework of the EMR, where perhaps at the end of the day, this could be implemented easily? So that's what we sought out to do, to marry these two major phenotypes into one. And what did we use to do that? Well, we used dense electronic medical record data on individuals followed for up to 30 years. And I want to point out, this is important because it's also real data, right? This is the type of data we have, clinicians get, and a way to track people. But can we actually use that raw data that may not be perfect in this context of creating this phenotype? And so what we used was data from the Mass General Brigham on about 60,000 people that we queried and had been followed up to this 30 years. And we decided to create this new variable where we're combining time till death and clinical and lab data in a phenotype that we are now calling EMR-age, and that is creating a clinically reproducible phenotype via the EMR that balances mortality and wellness together. And now, one thing I want to highlight here, we're just so far only talking about clinical data in the EMR, but I want to keep in mind for everyone out there that when we did this strategically, and that is because these individuals that we have electronic medical record data on are also part of the Mass General Brigham Biobank. And this comes into play in the next step. But keep in mind that this wasn't just people that we chose randomly, it was people who had biosamples in the Mass General Brigham Biobank. So for this first creation, what did we do? Well, we queried all these clinical labs that were available in the EMR. And when we did this, what we focused on were the primary labs that clinicians use all the time. So we looked through the labs, and it was about 50 to 60 clinical labs and phenotypes that we extracted from about 60,000 people. We had, not only demographics, and they aren't all included here, but a lot of the things from a lot of the panels, CBC panels, hepatic panels, lipid panels, basic metabolic panels. And we haven't even included them all here. And actually, as we've gone along now, we've added more and more and more panels. So we've extracted a tremendous amount of data from these panels. And at the end of the day, one thing we want to highlight is when we're doing this and we're creating this EMR-age phenotype, for individuals to actually be included in our mathematical model, they have to have complete clinical data for all of the labs we ran. So just think of this for people who and you're in EMR, take a person at a point in time. Do they have all of this information at one point in time or in a very narrow point in time? You see, it's very easy to lose people. So while we had all these clinical labs over a long period of time on about 60,000 people, when we look at them at specific time points, we lose people because of incomplete data. So we actually did this whole thing of balancing out completeness with size, and we ended up with about 30,000 people. And we looked in these 30,000 people, and one of the advantages of using the EMR is you may have them at one point in time, you have all this clinical data, but there's prospective follow-up. So you can actually see who's died and who hasn't. And in these EMRs, we have very well curated data on death that we've now combined with our EMR. So we actually do know that they died and why they died, et cetera. So we have pretty complete data on that. And from this, we use the clinical labs in combination with when they died after the time that we have this information to estimate their time till death. And from that, we take all of these labs and we see which labs are important, which labs are driving the prediction of our model. And that was a selection of these 60 clinical labs, and we see them here. And that basic model where we are predicting time until death using clinical labs is our EMR age. And here you see in this model, we can actually look and see what different variables were weighted higher and what variables were weighted lower in our predictive model and our estimate of EMR age. So this created our first estimate of EMR age. And what we asked then, and what is very important to think about is, we don't just want to create any value for this EMR age. We want to make sure that what we are creating for EMR age is the most robust, reproducible phenotype that combines death and wellness together that is out there. So what we then did is we looked at how we might be able to create this in all sorts of different frameworks to see how robust it was, how reproducible it was. And here are just a few examples. We looked at our value for EMR age and we said, okay, well, for some people, if we look at all the clinical data that were included, we maybe at first we required a very stringent 6-month time window of all those different labs. But if we relax that and we said, let's just say we needed those labs within a 5-year window, how correlated would the estimates of EMR age be? And what we saw here is when we tried to reproduce these, we saw striking correlations. And this is really important because let's say you're in an EMR and you have all of the data really close, but you only have one of those values that's like far away. You want that individual, you still want to be able to estimate it. And this is actually validating that, in those cases, we can still estimate this with really strong correlation. But not only that, we then did something else. We said, okay, we want to ask this question that if I took 4 different time windows in electronic medical record data, and I took all 60 of those labs at those 4 different windows, and I created 4 versions of our EMR age model, and they're all different. One's created at 2008, 2010, 12, and 14. But then I put my information in all 4 time points. You would hope that my EMR age comes up to be about the same, right? Because if I'm putting my data in, it should all be the same regardless of what clinical data we use to develop the model. And when we did that, what we saw was really striking. We saw that the reproducibility of this model was unbelievably good, that it didn't matter what time point we did. When we created this variable, it was remarkably robust with correlations from 0.98 to 0.995. I mean, these are almost perfect correlations, really suggesting that our EMR age variable is first in class. And this is very important to us because everything we are doing from now on is based on the premise that this variable And this biological aging phenotype is the best for not being one that's looking at age acceleration. We'll work on that later. So with that now, let's talk and see what we can see with our EMR age. And here's an example, and I'll explain what this graph is. I'm looking at EMR age and comparing it to chronologic age. Now, this is what's called a survival probability. So if we take each individual and we follow them for 12 years, we've divided people into groups. So if we look at EMR age and we see the orange group, these are people with our EMR age variable, we are saying are the oldest people. They are over 80 in our model. Now, we would expect people over 80 have the strongest, highest probability of dying. Whereas people who are in our youngest age group, less than 50, we don't expect them to die. And what we see is when we look at the probability of dying, or in this case, it's probability of surviving, among those who are the oldest, we say they die at a much, much faster rate than what would happen chronologically. So, for example, chronologically, by age 4, by 4 years from the time of the sample, you only see here that it's about like 22, 23% die. In our model, by age 4 years after, we're at, 35% die. And not only that, when we go out to 8 years, in our model, those who are oldest, we have 65% of people die. Whereas in the other model, we're well below, we're just hovering at 50%. So we're really showing striking that we are really able to identify those people who are dying faster. And not only that, we have perfect discrimination in those who are the youngest. No one in our model dies in the youngest group. And in chronological age, some people die, but not many, but some. Now, that's great when you compare it to chronological age, but we also want to look and ask about other aging phenotypes. So when we look at this and we compare this also to phenoage, which is the other clinical phenotype that is out there, we also see we perform far better. And actually, phenoage sort of performs like chronological age. So suggesting that we really are able to identify and discriminate people in an important way. So I want to ask other questions about EMR age. We also want EMR age. It's important to us that EMR age is relevant clinically, right? We want it to be associated with different disease outcomes. And here, this is a graph where we look at the risk of these different types of disease incidences within 1 year. And we see that in all of these cases, we have, associations with all of these chronic disease outcome areas. But not only that, when we look at EMR age and we put this in a broader framework of not just one year, but a broader time span, we see here that EMR age has much stronger associations with all of these chronic disease outcomes than phenoage does, suggesting that it is clinically relevant. And here I've highlighted in the back that the two that seem to be the strongest are cardiovascular and type 2 diabetes outcomes on top of mortality. So our EMR age is really addressing a lot of points well and much better than some of the other biological aging phenotypes. So at the end of the day, when we're talking about just the EMR, what are we able to do? Well, we're able to work within the current clinical system and capitalize on longitudinal EMR data. And, we consider barriers to broader implementation by really focusing on things in ways that this could be implemented easily. But we are able to create a robust and reproducible EMR aging phenotype. And this combines two things, wellness and mortality together, which really are the two things we are most interested in for healthy aging. Okay, so that's talking about this area of create. I want to now move over to the area of predict. And of course, this is what aging clocks are all about. They are all about, can we estimate and predict biological aging well? And I know a lot of us are familiar with this area, but I want to talk about this area in the framework of our new our new Omic MH phenotype that we are using in this predictive model, and talk a little bit about how it's been developed and why this is so important. But why it's so important is fundamentally also related to the next area, which is understanding. But let's talk a little bit about predict. Now, everything I'm talking about in the framework of prediction now, we are talking about predicting our EMR age that we just developed. And I want to step back and just ask this question, because this is, of course, a big premise of why we create prediction clocks with the Omic data that we do. And that is asking this question of biologically, what's happening when we age? And we know that the epigenome is really the biological framework of aging. These molecular changes are what is responsible for our biological aging. But I want to highlight just very briefly what that is in an analogy here to make sure that we're all on the same page and understanding what exactly is happening. And I want to give this analogy with banana bread, where over on the left here, we have the ingredients of banana bread. And on the right, we have the recipe. So imagine that the ingredients are genetics and the recipe is epigenetics. Now, the ingredients never change. The ingredients are the ingredients. The ingredients are your genetics. And they are my genetics, and those are staying the same. But with aging, what is happening to the epigenome? And over time, what is happening is you can think of it as if you took this banana bread recipe and slowly over time, parts of it start getting difficult to read. And as things are getting difficult to read, the ability to make the banana bread becomes less and less. I mean, you're still making banana bread, but what I'm seeing in the recipe right now and how to make it isn't going to turn out quite as well as when we had the full recipe. And this idea of alterations to the epigenome causing our biological aging is really fundamentally what is happening. And ultimately, this may cause unreadable parts of the epigenome, and that causes aging. So I want to highlight this because if we now think of this in the framework of epigenetics, we can think of this, and we may take the epigenome of a 20-year-old and a 60-year-old, and you may see that what's happened from 20 to 60, particularly for DNA methylation, which is a type of epigenetics, is that there are these changes in methylation, where in some cases things may go from hypermethylated to hypomethylated. The main point is these may be changing up and down, but they are changing. They've not stayed the same. And these are examples of where the recipe isn't being read right. And so now the level of methylation is off. Now, what has happened in the field of aging happened, well, quite a while ago, we recognized this association between epigenetics and aging way back to the 1960s. It was in, about 10 to 12 years ago that Steve Horvath was a senior author on one of the first papers demonstrating the striking association between DNA methylation and chronological age. And I remember sitting in the American Society of Human Genetics when he first presented this, being astounded by this correlation. And of course, now it is a whole field from this has exploded. And here we see in that initial paper, this strong correlation with chronologic age and your DNA methylation. And as Varun reviewed quite at the beginning now, there's this whole explosion of biological clocks that started with the first generation chronological clocks, moving to the second generation aging clocks that are based on biological aging phenotypes. And again, the third generation, and in this second generation, I want to highlight, as we've talked to so far, the clocks of Grimm age and phenoage, which are the clocks based on phenoage itself, so the DNA methylation predictor of phenoage, and the Grimm age clock, which is DNA methylation predictor of time until death, because we will be referring to those as we go along. But of course, along the path of all these epigenetic clocks, there's all sorts of clocks that have been created to understand systems of the body, et cetera. But I want to talk about what we now did with DNA methylation, just starting with that, and our EMR age variable. And that is, remember I said at the beginning, when we created EMR age, we were very strategic in that we looked at these 60,000 people in our creation of it, because they also had samples in the Mass General Brigham Biobank. So we took those EMR age and we identified 5,000 people in our biobank. And I pulled those samples and sent them to True Diagnostic, and we generated DNA methylation on these 5,000 people with the idea that we would then create the first EMR age DNA methylation predictor. And that's what we did. And I won't go into all the details of it, but this is, a very basic, AI predictor where we are doing, doing AI to create a DNA methylation predictor of our EMR age and using lasso penalized regression of the CPGs. And I just want to show here that, with DNA methylation, the prediction and the accuracy of this is really quite striking, right? Our correlation in this predictive model is already over 0.9 to begin with. And so this is really exciting to see as the beginning of the study that we're already getting such good predictive accuracy with DNA methylation alone. And, DNA methylation is just one drop of blood. And that's an important biological metric. We've already talked about the fact that we know that, the epigenome is responsible for aging, and DNA methylation is one of the forms of epigenetics. But as Varun highlighted earlier, by golly, aging is a very complicated process. And while there's all these things we can look at here in terms of different ways that we know molecularly we age, we look at all of these things from telomeres to epigenetics to senescence, cellular senescence, et cetera, inflammation. We know that this is a very complex process. And while we're able to predict this very well with DNA methylation, is it important to consider other types of molecular data? And so this is really the next point of our query and quest, was to look at these individuals, these 5,000 individuals that we have DNA methylation on, and see if we added other molecular data, what we would then learn further. And what's the concept behind this, right? Well, the concept behind this is, of course, if we go back to, the theory of DNA going to RNA, going to proteins, going to small molecules, we know that all of these molecular data are interconnected and interconnected in important ways. And perhaps if we understand multiple levels of the molecular data, this can give us a much better perspective of what's happening to us as a biological system. And so let's just think about this. If we could consider the idea of, can we take genetics and can we add the epigenetics that we have? Can we add on gene expression through the transcriptome, where we see what genes are being expressed, to proteins, inflammatory proteins, all these proteins we know are good biological markers of aging, to small molecules through the metabolome. We know this is a major, some of the best clinical biomarkers, from blood glucose levels to measures of inflammation, LDL cholesterol, et cetera. And, well, we didn't do all of this. I want to put it in this big framework, because as a researcher, this is how I'm thinking. Can we look at other things? Can we look at things like microbiome, gut microbial health, dysbiosis? Can we look at exposures that, we've had and that are measured in our molecular profiles? And can we look at the phenome, what we're calling the phenome? And this also is reflected in electronic medical records, right? Can we look at the clinical data that we can extract from electronic medical records. And fundamentally, the idea of me as a researcher is, can we take all of this information and can we look at this all together in individuals at one point in time, synthesize that using systems biology, AI approaches, machine learning, to inform us about things like aging. And this concept, when we're looking at all of these data together, this molecular data, each one called its own omic. So together, the multi-omic can give us this multi-omic profile of individuals and help refine and understand why different people are aging at different rates. This is precision aging. This is what it's all about right here. And so while we can predict things, the concepts and the ability that we can do with all this multi-omic data is far, far beyond prediction if we can actually generate these data on everyone. So, okay, let's talk about the next thing that we did. Okay, so we have our 5,000 people with epigenetics, which is a huge number. We have, EMR age on all these people, plus a ton of clinical labs, clinical data, right? But what else did we, set out to do? Well, this has been sort of a mission of mine where I'm slowly trying to amass data within the Mass General Brigham Biobank system that has EMR data. And if you look at this over to the number of individuals within my own collaborative, my own lab, this is data that we have access to, which is clinical labs on, all of these people, 30,000 people over up to 30 years from the EMR data, whole exome sequencing on 60,000. And actually the clinical labs we actually have on 60,000 too. Transcriptomics, we don't have mRNA itself, but we have microRNA. We have our epigenetics. But for this project, what I want to focus on is the epigenetics, proteomics, and the metabolomics. And you'll see here over in the total number of individuals, our numbers for proteomics and metabolomics are higher than when we go all the way over to the left and we see the numbers of what we actually used for omic age. And that is because we are continuing to generate these other omics. So for what we're going to be showing you on omic age, we used the data that I have summarized over here to the left. 5,000 for epigenetics. Everyone has EMR age and a ton of other clinical data. We have 1,500 for proteomics and about 2,000 for metabolomics. So what did we then do? Now, we looked at how we created the DNA model, predictive model for EMR age, and that's done, using sort of the standard approaches that have been used in this area of biological aging clocks. But now there's a few other quandaries, right? Because number one, we have a ton of data, but not only do we have a ton of data, the data all behave a little differently. And from a statistician like myself, it's not, we really can't just shove it all in a model. We have to be thinking about this in a systematic way. But I want to say here, if you look at this framework, the whole goal of what we want to do here is to create our new omic age predictive model using proteomics, methylation, metabolomics, and all the other clinical lab features that we have together with EMR age to create our overall omic age phenotype. Now, when we do this, I do want to highlight that this is a complex process. And when you start adding other omics, it becomes more and more complex. And this is an area that I think fundamentally it's important to us to understand that we need to go from something that's complex down to something that is simple. This, to me, is a crucial step because while we can use a lot of data to generate what we want to at the end of the day, what we generate needs to be something that we can measure very simply. And this created among us the concept of creating DNA methylation surrogates for our Omic data. And by doing this, what we're able to do is take all of the Omic data, combine it together in a way that we are then able to, at the end of the day, have one simple DNA methylation model that uses all the Omic data. And let me show you how we do that. So I showed you we had all these Omic data to begin with. And what we did was we said, okay, let's take all the proteomic data we have and all the metabolite data we have and a bunch of clinical data that we have in the EMR. And let's identify different types of metabolites, proteins, and clinical variables that we know are associated with EMR age. We can just do that through correlations. So once we get that list of proteins, metabolites, and clinical features, what we can then do through AI approaches, using things like lasso regression, we can create a DNA methylation surrogate of each of those things. So that's what we did. We took our DNA methylation data, we took our proteomic data, we combined it together, and we created DNA methylation surrogates of each of the important proteins, the important metabolites, and the important clinical variables. And as you see here, there are 107 proteins that were important. There were 267 metabolites and 21 clinical variables. And here's just examples of what I mean, just to put this in your framework so you can sort of understand this. Okay, so we have DNA methylation surrogates for things like, for proteins, we have things like albumin, IL-5, H1P, all of these different types of proteins. For metabolites, we have DNA surrogates of things like DHEAS, serotonin, cysteine, cortisol, uridine, carotene-diol, and DNA methylation surrogates for the clinical data on things like hematocrit, HbA1c, triglycerides, glucose. And so you see, if we did all of those surrogates, here's just an example of what those surrogates look like. These are the correlations of the surrogate with the actual value itself. We can now take all those DNA methylation surrogates, put them all in a model with a DNA methylation. And at the end of the day, when we do that, we can create our Omic M age. Now, I want to highlight in here, I didn't highlight this to begin with, but in our model, we did want to strive for best in class, and we just published a paper on actually also incorporating better immune deconvolution with a 12-cell immune deconvolution. So we also refined even the way we are deconvoluting the immune cells in this Omic MH. So now you have it. Now we have an Omic MH clock. It's incorporating all the important proteins, metabolites, and clinical data with DNA methylation into our Omic MH. And beautifully, we can now measure this on any individual just by running DNA methylation, which makes this test affordable. That is important, right? Because if we did all the tests, it is not affordable. But let's talk a little bit about how it actually predicts. And as you see here, our predictive accuracy is about it's 0.91 in the training, and then at the testing set here, it's also 0.91. So showing very, very robustly that it is predicting very well. So this is a good sign. But other things that are important is not only how well it predicts, but of course, what's more important is its relevance to disease outcomes. And here we see that when we look at this, the Omic MA has the strongest associations with all of these disease outcomes, all-cause mortality, type 2 diabetes, stroke, CVD, depression, COPD, and cancer is the one it's not doing quite as well as, I think there's some reasons for that. But what I want to highlight here is if you look at this, the purple are our two clocks. They're DNA M EMRH and Omic M EMRH. You see both of them here, and that in all these cases, it's actually regardless of which one we choose, we see that ours are performing far superior than any of the other clocks that are out there, whether it's GrimAge, PhenoAge, and a bunch of these other clocks by Hannam and Horvath. we see that we are having much stronger associations with clinically relevant outcomes. And that's important. But the other thing we want to highlight is really overall, if we're looking at things like mortality, which ones are best? And these are what are called ROC curves, and these are looking at both the sensitivity and the specificity for predicting mortality. And we have a 5-year mortality and a 10-year mortality. And basically, the further it goes up and over, the more accurate it is. And here you see, in our case, we have omic age and DNA M EMR age here in purple and orange. And again, here we see it on DNA M in purple and orange. So by far outperforming all the other predictors. Now, so this really is encouraging that we see here now our omic age, MH, is showing high predictive accuracy. Now, I want to highlight here that its predictive accuracy is pretty much on par with DNA methylation age. And that is actually important. And there's several reasons for that. I think one of them is that in and of itself, there's a lot of predictive value in DNA methylation. Another one is, I think there's other ways that we look at this where you see these differences are so small, where we see that omic age is much better than DNA methylation, as in some of that disease outcomes. But I want to highlight even more why what we are doing with all of these other omics is so fundamentally important, because we're just stepping at the beginning part of this. And I now want to go into other aspects of why this is, the omic age is so important, and what else we're able to learn and take from this. And this is one of the things that Steve Horvath had said here, that this whole second section is on prediction. And we want to remember that when we are looking at a predictive clock, they are not always causal. What's in the predictive model is driven by AI, machine learning approaches, and they're not always causal. And extracting meaningful biology sometimes can be challenging. And, it is often that sometimes in these predictive clocks that the clinical implications are limited. And this is a major weakness of machine learning algorithms like what we're using in prediction. So that goes to the last part of what I want to talk about today, and that is understanding. And I want to talk now about how we can take all of what we've done to develop our omic, our DNA and our omic EMR age-based predictive algorithms in the context of what the importance of how we can now use omics to really, really ramp up our understanding, and why that is so fundamentally important in this next part of not only going from prediction, but going to the next step. And, there's a lot of companies now that do predictive algorithms, right? And I don't think any do them as best in class as what I've shown here today, but prediction is one thing, but taking it on to this next part where we really can extract important biological meaning is critical. And this is where we are now doing this in a way that I just haven't, this has not been done, and we're really on the realm of new discovery here. And when we think about this, right, we've now created, this EMR age predictive models. We take a drop of blood, we measure, your omic age, and we can immediately give you a good sense of what your overall biological age is. But can we identify causes of biological aging? Can we prevent biological aging? Can we reverse it? And if we just stopped at prediction, the answer is no. Unfortunately, we can't. We may, in terms of general things, you can exercise more, you can eat better, you can do this, but it's all general. This talk is about precision aging. It is not about aging in general. So what we now want to talk about is how we can now take this and understand this on a precision aging framework for each individual, right? And that is what we want to do. Can we actually look at this and give you the specific advice, or your patients the specific advice of what they need to do? And so that goes into this idea of really characterizing real effects that we see with DNA methylation. And I talk about this idea that, when we take DNA methylation or a lot of the other types of epigenetics, it is very often hard from going from that to understanding. And the key reason is because we're just looking at hypermethylation, that's not giving us a lot of information. But don't forget, in what we've now generated, we've generated metabolomic data, proteomic data, and we have clinical data. We have all sorts of rich information now that we have DNA methylation surrogates for. So for anyone who comes in, right, and you get your Omic age done, we also have methylation surrogates that give us a lot more information about what's actually happening biologically. And with that, we can, the important thing is with things like proteomics and metabolomics and clinical data, that is really what we need to bridge the gap between methylation and aging. Now, putting this in the broader framework of how do we do that? So let's think about how we can use those omics to bridge this gap in our understanding from what we see with epigenetics to what we understand about aging, with things like the proteome and the metabolome. Well, we can take those, and now with what we've done with omics, we have a very good sense of what the proteins and metabolites are doing and their individual associations with EMR age. We can see that now. We see things that have strong associations with EMR age and whether they're increasing it or decreasing it. And, we can see things like metabolites in the energy cycle, metabolites of frailty. We have specific biomarkers like this one, vinonylic mandelic acid. We see things with dysbiosis of the gut microbiome. We see different markers of kidney disease. We see different inflammatory cytokines. And the point is we can use all that now and understand how that relates to DNA methylation. I also want to highlight here, not only can we understand those molecules, but we can also understand a lot of deleterious exposures and things like PFAS or other exposures that we know are bad for aging. And now with what we now have with our omic data, we can actually say, we can look at these different individual omic variants, whether they're proteins or metabolites, and we can say, and as you see here, if you look at the picture, as I do this cartoon going forward, you can see how I'm trying to put together understanding with the molecular data with DNA methylation. PFAS may increase inflammatory signals and increase aging. Good microbial metabolites decrease aging. Cotinine is associated with increased aging. It's a biomarker of smoking. Endogenous steroids reduce levels, increase levels, decrease aging. Good food, things like L-serine and omega-3 fatty acids are going to decrease aging. Other biomarkers we know for aging are going to be associated with increased aging. Serotonin is going to decrease aging. DMTPA is going to increase aging. And these are just a very select group of the overall molecules that we saw that have strong associations with EMR age. And from this now, we have a much better global picture of how we can understand what's happening with your epigenome and the different ways that biologically we are seeing associations that then we may be able to do further research and understand causation. So put simply, omics bridge the gap from DNA methylation to biologic understanding. And when I talk about this, I want to talk about this, that this is all now something that, well, we did this and we mapped this all together with the omic data we have in our cohort. And we will continue mapping that. Trust me, we aren't done. When we go to each individual, we can measure surrogates of these things in each individual. And that gives us an idea for each individual of how they uniquely may have contributors to how they are aging. And this is a very simple way to understand and extend our biologic understanding. So we've now gone through and we've seen how we can create a biological aging phenotype that is best in class by putting together both the clinical and the mortality data together, wellness and mortality, to create our EMR age. We've shown how we can predict it with not only DNA methylation, but also putting in these DNA methylation surrogates of the other omics to create this multi-omic aging predictor. And we now see how we can use all of those omics to really further our understanding of the disease processes that are impacting our epigenome. Now, I want to highlight that we are like just at the beginning. There's so much we can do with the data that we haven't even touched upon, that our understanding is really at the beginning. And I think this field as a whole, there's a lot of understanding that's really at the beginning. And I'm excited to see what we continue to learn as we continue to delve into the multi-omic data that we have. But I want to go back to this, right? Because this all comes back to the idea of precision aging. And we've looked at all this data, and what I want to highlight now is, when we are looking at what we have now with omic age and the omic data and DNA methylation surrogates that we have developed, we are really uniquely positioned to take each person and ask from a precision aging framework what their EMR age is and what is being affected for them that may be driving this, not only from prediction, but also going more into association and hopefully leading you even further into causation. And it's really about then getting to this EMR picture I see here, where we can then look how we can look at the totality of health in aging and optimize it with our aging predictor and omic data.
Well, once again, we're at that point of our educational program that to me is the most exciting, because it really allows a kind of free-form discussion among the key opinion leaders on the topic of interest. And new things always arise out of these conversations that maybe were unscripted and but really are news to use. And so with that, let me just set the tone for this next 30 minutes by saying that I've been around in this field a number of decades. And over that period of time, I'd have to say that I consider myself pretty much an early adopter of many new technologies. But because new is there, it's a shiny object often, and it attracts you to it, but it doesn't mean necessarily that new is better or new is more practical or new is more valuable. But in the case of what we're talking about, the evaluation of the methylome, and how that connects to understanding of epigenetic determinants of gene expression, I think new in this case is valuable. New is really important. And I think we're seeing a sea change in the whole ways that our genetic potential is being evaluated based upon the interweaving of our genetic template book of life, 23 chapters encoded in our genes, and then how they become imprinted and ultimately affect in the phenotype the outcome of individual's function. And I think this particular educational program will be looked at in the future as being really a harbinger of a whole new perspective as to what is valuable in understanding and setting kind of a tone for sequential analysis, because the epigenome, as contrasted to the genome, is to some degree modifiable over time based upon environmental, lifestyle, and circumstances of daily living. And so what we are starting to witness is the ability to look at the flux of the genetic information that ultimately creates the outcome that becomes us as it relates to our phenotype. And so to me, this particular program is a little reminiscent to when I, in 1999, authored the book Genetic Nutritioneering and was talking about nutrigenomics at a time where most people thought, well, what the heck is that? Is it really just a kind of a buzzword that has passing fancy, or is it a concept that's here to stay? And I think what we've learned from 1999 to 2023 is that that was only the front edge of a paradigm shift in the whole nature of the way we see nutrition and its relationship to health, as will be the understanding of the epigenome and how it's modified and how to evaluate it through assessment tools and the deep sequencing information that also comes from informatics that we have available to really analyze very complex data sets that give rise to information that we would previously not have access to. So with that as kind of an introduction, let me throw the question out to the two of you, my extraordinary experts in the field. So as you start to see the people starting to pick up on this technology, what are the most common things that bring the people into this technology and the things that limit the use of this technology as it relates to their present understanding? So Ryan, maybe we'll start with you and then move over to Jessica.
Yeah, certainly. I think that, in the lectures that we've given up until this point, we've talked a lot about aging and methylation, but also now I think in these things we're calling sort of methylation risk scores or epigenetic biomarker proxies, because, and I think this is a really big step forward from previous lectures in epigenetics. And the reason being is that we're starting to get a clinical resolution that can really match up to prior content and knowledge that physicians have been trained for. Right now, I think these epigenetic biomarkers have been in really abstract concepts, which are really hard to manage sometimes, like age, for instance, biological age, which is a really complex topic. But I think one of the biggest takeaways now, which is making this really clinically applicable, is that we can also have these surrogate markers for these proxy markers for things that clinicians deal with all the time. Things like HbA1c or C-reactive protein, these things that are very well known and notable, but we can view them through a lens of epigenetics. And in the case of sort of the Omic age algorithm that Dr. Lasky-Su talked about a little bit earlier, we can combine them all into one model, which can inform us about really complex processes. And so I think that previously epigenetics has been held up by a lot of caveats or limitations, a lot of things that say, accept this as a marker, but without these 20 use cases where it might not be accurate. And I think that now we've sort of got to a point where we can report on really complex phenotypes like aging with really high degrees of resolution and without those caveats, but we can also then give the why in ways that clinical practitioners can really understand and modify. And so I think that I'm really excited to see, this go forward. Even just previously over the last year, we've really had these epigenetic proxies really be available and now incorporated them into these really big models like aging, which now can I would say give us some answers on how we might go and combat that process of aging. And so I think that, we've talked a lot about sort of how methylation is changing in these lectures, but I think that one of the big milestones are these epigenetic proxies, where we can look at the gene expression markers which are changing and correlate them to changes in phenotypes. And so I think that's a really big thing that hopefully these lectures have sort of talked about. And now I think hopefully all these practitioners can go back to their clinic and see how they fit in with all of their practices, not just in treating age, but I think in treating risk across the board with one single biomarker as a detection marker.
Jessica?
Yeah, so building a little bit on what Ryan said and also what you said, when we go all the way back to looking at genetics, right, being in this field for, 30 years or whatever, one of the things that I've observed is you can identify, genetic associations with whatever disease, but actually having any practical way to change or modify behavior to affect risk or reduce, chronic disease outcomes, et cetera, is really, really challenging. And I think that's what's limited the entire field of genomics as a whole, because that step is so challenging. Once we get to looking at epigenetics, we now are sort of understanding that this is a basis of how our biological genome is changing with age. And the question comes, how can we prevent it, right? But the challenge there is understanding why. And what Ryan just said, this concept of connecting the epigenome to actual clinical data or phenotypes to help us understand how we can change it and what specific ways we can see the interactions between the epigenome and other phenotypes that we may know how to modify. That's a really, really critical step in clinical translation. And in doing this, one of the things I want to highlight is, we often think about, okay, we have these traditional biomarkers that we understand affect health, like Ryan said, HbA1c, glucose, cholesterol, we know these affect health. But now when we're in this new Omic era, there are so many other things that we can capture and measure that probably we may not even have the best biomarkers of health yet, but they may be coming. And with the way that we are now looking at sort of epigenetics in combination with other Omic data, right? Other deleterious exposures, other ways that, our body is changing metabolically. if we can then now identify perhaps even novel clinical biomarkers, and then link them to the epigenome, that is going to be a crucial step in understanding how we can change both the aging process and reduce chronic disease burden.
You know, what you both have said is really powerful, because the way most of us have learned about use of laboratories and assessment is around looking for downstream smoke that then tells us something about the fire. These are secondary outcome principles from something going on upstream at the cell biological level. So when you look at virtually any biomarker, you're really doing downstream kind of outcome-based assessment, which is circumstantial, but not definitive as to what's actually going on at the cell-based level. And I was very struck when I read Sid Mukherjee's most recent book, The Song of the Cell, which is on cell biology, which he thinks is really the currency of the change in all of medicine, is that we're moving from a whole organism kind of anatomical perspective to a cell-based model in which we start to really understand the physiology of cell biology at cell-specific levels, and how that then regulates ultimately the phenotype of the individual. And so if we want to get upstream information to tell us something about what downstreams impact the exposure that an individual has to their life, then we want to do something that is going to be the controlling factor for what goes on downstream and regulates inflammatory cytokines or glucoregulatory hormones or whatever the biomarker might be. And that is really the epigenomic control over genes that regulate the cassettes of genes that control those functions. And so I think that this epigenomic revolution, now that we've moved away from the static view that epigenomes are only really important in infancy and fetal development, to where we now see that we have plasticity in the genome to some extent for epigenomic modulation throughout all of our life, and that those then regulate downstream functions that we tie euphemistically to the concept of biological aging. But biological aging to me is just a placeholder for really understanding upstream influences on cell biology that influence our functional health. And that is really where the currency of the realm resides. If we want to really improve health of our population, it's one person at a time getting their cells to work more effectively in the environment in which they're living, to produce not the alarm molecules, but the molecules of resilience. And I think that's partly what we start to understand from epigenomic analysis. So it's a whole paradigm shifting concept. And I worry a little bit that this concept will be high-centered for a while around age, because I think age, as you said, Ryan, is kind of a proxy for a much deeper understanding of what's going on at biology at the cellular level, upstream to the downstream effects that ultimately we measure in the diagnostic laboratory. So maybe you two want to have a whack at my philosophizing here, but that would be kind of my thought. So how about you? You want to have a whack at that concept?
Yeah. So I'll say a couple things. So I think one of the points you just hit on at the very end, I think, is critical, and that is the concept of specificity, right? By nature, like, I think of a lot of the biological aging phenotypes as a really large measure of overall chronic disease burden. I mean, essentially that's what it is. And it is incredibly good to look at that overall, but ultimately we have to get down to specificity. And whether we're talking about specificity of a specific disease outcome, or like what you were saying, specificity on the level of a cell or something along those natures. Those are two different types of specificity. But I think you're right in that right now there's a lot of focus on overall epigenetic clocks for aging. I will say, from a research perspective, there's a huge focus on epigenetics with much more specific disease outcomes. And I think that the aging field is going to move that way, because they have to move that way in order to be clear about preventative measures, right? You can only get so far when you're looking at a broader measure. You have to look at much more specific measures in order to really capture ways that we can modify things for specific disease outcomes. So I think that's one thing, I want to highlight. Another thing that I wanted to highlight in what you were saying is, this concept of time, right? And plasticity and ultimately, one thing causing another thing. I think as people who are like myself, who's in research, one thing that is incredibly important is that we don't just look at this in terms of a static time point, and that we really are looking at things over the course of time, because that temporality is really what helps us understand prevention, rejuvenation, and all of these mechanisms. And so if we can actually look at things in that perspective time frame, or over the course of time, we can get a lot better understanding of what's happening on the cellular level as a disease progresses and as a specific disease progresses. And those are the types of things that are ultimately going to get back to causality and prevention. So I think that's really incredibly important in the way that we need to continue moving if we want to move really into the preventative space on a massive level. I think that's what we need to be doing.
Right?
Yeah. Yeah, and to add to that, I think that that's why I'm so excited about some of the tools we've developed with this Omic Age calculator. I think that we did it as a way to help inform more complex aging biology. So we wanted proteins and metabolites to be included in this really complex definition of age. So it's capturing more of that biological picture. But I think a lot of the tools that we developed can help inform methylation risk scores across multiple diseases. And I think that's why I'm so excited for some of these tools to be then applied to other areas, and even to get outside of aging to more disease-centered processes, which are obviously, things insurance reimbursed and obviously well characterized and ways, and it actually considered a disease, unlike aging, as it relates to the FDA. But to give you an example here, there are a couple of things I like to show. One is that previously some of these age calculators like GrimAge, they added surrogate predictors. So for instance, GrimAge version 1 predicted about 10 proteins. In version 2, they only added 2 additional predictors. They added HbA1c and C-reactive protein. But when they did that, their prediction of age-related diseases got even better. Those hazard ratios of disease got better because they were capturing more of this biology. And so for us, what we've done is we've predicted, metabolites, even nutritional metabolites. I know, Dr. Bland, you're a big proponent of food as medicine. And what we're doing now is quantifying even some of those different metabolites from, for instance, diet, things like ferritinediol, which we know improves biological age, or uridine, which improves biological age. Those are some of the things we found as some of the biggest predictors in this overall model of age. But this doesn't have to be the case. We can also add HbA1c and fasting glucose and, several other metabolites to disease prediction like diabetes. And already with diabetes, there have been great published papers in epigenetics that can just go from a type 2 diabetes diagnosis to actually a type 2 diabetes diagnosis with a subtype category, where they might have different risk factors or different treatments. And this was done in a university, Lund University out of Sweden. And we think that our methylation risk scores, or these epigenetic biomarker proxies, as we're calling them now, can also be used to help influence and give us resolution on disease categories. And so we think that combining all of this data together can really develop these tools and really accelerate us quite quickly in this space of epigenetic methylation, where we can really go from having these really complex phenotypes, but also having the tools in the underlying training to give a lot more resolution and a lot more clinical guidance on what we're really seeing there. Type 2 diabetes might manifest in a lot of different ways for people. Some people might develop peripheral neuropathy. Others might have more cardiovascular related events. Others might have, different visual things in their eyes. And now maybe with these epigenetic methylation signatures, we can start to have so much resolution that we can predict these things really early. And that's why I think that this multi-omic data that we generated is just so valuable, especially combining it all into one biomarker that can really be a simple and easy test, but inform us on a lot of different outcomes.
So you really cited something there that I had a flashback a number of years ago. It probably was like 6 years ago. Dr. Joel Dudley spoke at our PLMI meeting. He was at Einstein School of Medicine at the time. And he had published a paper that was showing that when you did omic analysis of type 2 diabetics, you could subcategorize into 3 different classifications. and you start to get a much more finer cut on not only what would be the therapeutic potential for the benefit of that individual patient, but what would be the potential outcome of that person that you should look at in terms of their phenotype, as you were indicating, cardiovascular, neurochemical, immunological. And so I believe that the sequence of evolution, or the process of evolution of ideas within the epigenetic field right now, and I want to really I give a very high commendation to True Diagnostics for being a pioneer in this area of assessment. It's with some risk that you always take when you move into a new assessment area, that you're going to have the burden of both developing the technology and educating at the same time about the technology. And I think True Diagnostics has done a superb job in managing those two challenges or responsibilities. But the technology you're developing, as you've indicated, has a much more granular and precision capability for understanding exactly at the level of where these dysfunctions occur and how to modulate them upstream of what we have to wait often for the downstream effects at the cell pathology level. So I really think that what we are witnessing, and I guess the question I would like to ask the two of you is, as we see the development of this technology of using the methylome as the assessment guidepost for epigenomics, knowing that there are many other processes that can relate to epigenetic modulation of the genome, what do you feel about the methylation technology? It's certainly, from a chemical perspective, one of the easiest to access because of the technology for its assessment. But is it going to prove out to be the principally beneficial way of assessing epigenomics, do you think, using the methylome?
Yeah, and Dr. Su, I might go first on this before I throw it back to you, especially given your experience in the other omic platforms like metabolomics. But I think my answer would be yes. I think that one of the other things that was actually really informative about the work we did with Dr. Lasky-Su's lab was that we were actually able to look at not only our successes, where we could use methylation to predict things really well. One of those categories is things like functional spirometry. We had great ability to predict functional spirometry like FEV1 and FVC through methylation alone. But we also had areas where we weren't quite as successful in things like, for instance, plasma lipids, where we were looking at different types of fatty acids. And so I think that both the strengths and weaknesses are a little bit of an answer to the question, where I think that the methylation technology will do very, very well at covering a good percentage of some of these outcomes we might want to look at. Maybe spirometry is a really good place for us to start. Maybe looking at complex diseases like COPD or interstitial fibrosis, because we know there's such a link to some of those functional markers, and maybe staying away from some of the more lipid-centered diseases, because we know there's not as much of a correlation. And so I think that the DNA methylation technology has been really limited by a few things. One is certainly scale. There are 29 million different locations, CpG locations we could look at in every cell, and every cell has a vastly different phenotypic expression. The other is those cell type issues, where we're looking at DNA from multiple cell types, which can confuse these algorithms. I think we've come a long way in that, which is why we're now getting to this point where these methylation algorithms can really be used in the clinic. But I think that there are still obviously some limitations, which will never get past the fundamental logistical concerns of what is DNA methylation. And there, I think that that's why we're so interested in this omic analysis, is because it can really help compensate for some of those weaknesses.
Yeah, so adding on that a little bit, I want to go back to just briefly talk about the concept of disease subtypes and disease endotypes, because fundamentally, to me, this is such a crucial topic. And I will say, as someone who is really based in looking at chronic disease, so much of how we think of it now is that, any disease area, whether it's diabetes or asthma or obesity, it is not just one disease, right? Within that disease, there are disease subtypes, and those different disease subtypes have distinctly different etiologies, which is why you can't tell the same person to do the same exact thing and expect the same result, because some of it may be differences in underlying genetics. Some of it may be their environment, and some may be an interaction of the two. So in thinking, just going back to that concept of this complexity, the fundamental thing that I think we have to think of and understand is, with that, it's so crucial to understand and get some type of capture of data that ultimately can reflect multiple levels of systems biology, right? What's happening, in inflammatory proteins, what's happening in metabolic function, what's happening in epigenetic modifications. And so the thing that we've done now with Omic Age that I think is really where the field is moving is, can we actually capture these different levels of what's happening biologically in a way that is financially feasible? And to do that right now, we're doing it with DNA methylation. And the primary reason is ultimately, it may not be the best predictor of everything, like Ryan said, but fundamentally, that is at the core mechanistically of what is changing in the body. So I think just because we know biologically that is the most relevant thing, I think that's logically what we want to be always going back to. But by doing it in a way where now we're saying, okay, we recognize we can't really capture with just DNA methylation all of the changes that are happening in the proteome, the inflammatory proteome. We can't capture all of the metabolic changes or all of the sort of nutritional exposures and other exogenous exposures we have. But what we can do is we can use AI techniques. If we have a larger group of data where we have all of those inflammatory mechanisms, all of the metabolic measures of the metabolome and the genome, if we have those in one study and then we use AI, we can estimate all of those with the epigenome. Now the epigenome is serving as this proxy where it's not just reflecting the epigenome itself. We're now adding onto it a layer and perspective where we're capturing those inflammatory proteins, we're capturing metabolic function, we're capturing nutritional exposures and other exogenous exposures. Boy, by doing that all together in this AI approach where you have all of these proxies and you're synthesizing it together. Now, okay, granted, you may not be able to get lipids good, but if you can as well, but if you can get 80% of all of those other areas of systems biology, now your power to understand biologically what's happening and go all the way back to specific disease subtypes is tremendous. And that's what we've done here. And I think these approaches are going to be critical into continuing to go forward and understanding not just general disease diagnoses, but specific ones that we can then use to inform treatment.
That was brilliantly stated, and I absolutely 100% agree with you. And I think that you just spoke to the future. You spoke into where we're going. And it's not that we're going to leave behind and never once again look at downstream analytes, but I think that this is part of a new, much more broad time sequence perspective about how to understand trajectory towards health and disease. And I'm reminded, I'm holding in my hands right here, actually, this is 1 week of publications on the methylome and its relationship to functional health. And at least 1 week of articles that I chose to download and read. And one of those articles, which bears on both of your comments, has a very innocuous title, but has a very deep potential significance. It's entitled, "Grip Strength is Inversely Associated with DNA Methylation Age Acceleration." So what that means is people, as their grip strength goes down, their methylation age is increased. Now, does grip strength cause methylation age? No, it's a phenotypic variable that relates to strength. Strength relates to all sorts of physiological functions, many of which are powered by mitochondrial oxidative phosphorylation, which are processes metabolically that are controlled by epigenomic modulation of energy producing components of our cells. So, we start to really see these associations become guideposts for how we're going to actually use and understand what's going on in a patient that might appear to be very complex, but its upstream influence may come as a consequence of modifiable influences of their epigenome. So that's a different perspective entirely of how we do assessment. We're not diagnosing anything. We're prospecting an understanding, interrogating function at a level that we didn't have access to before.
Yeah,
So,
and I like. Yeah, so I think you're totally right, and I wanted to maybe show another study out there that's probably a little bit lesser known, but there's actually a great study looking at subclinical atherosclerosis. So being unable to diagnose it via traditional measures, and still show the same epigenetic age acceleration link between even subclinical factors. And the reason I say that too is because I think that when we're looking at a lot of these epigenetic algorithms, we do have that question of cause or effect. I think, Dr. Bland, as you were talking about, and I think that in some cases, particularly in this case, we could see that sort of answer the why. Why are we seeing epigenetic age acceleration in subclinical atherosclerosis? And this eventually was with other omics like transcriptomics and metabolomics linked back eventually to inflammatory processes, inflammatory burdens early in life that then led to this subclinical development, but was still able to be seen in a biological age process before it was able to be seen in classical clinical cardiovascular biomarkers. And so I think that, again, going back to that, I think that it's interesting to see that these things are happening in a way that is distinguishable through these biomarkers, even early. And I think it also adds credence to why biological age is so important, is because it connects to functional declines, like you mentioned, in terms of grip strength. It connects to molecular, I would say, differences that are out of range, things like inflammatory biomarkers. It connects to neurodegenerative outcomes. It connects to almost every phenotype that we would see. And it's why we like epigenetic age as a surrogate. I think that going forward, we certainly want the resolution into disease processes. But for one big biomarker, I think hopefully epigenetic age is able to consolidate a lot of those negative changes that occur, not just with age, but even disease processes.
So Jessica, Ryan just gave us a lot of news to use there. I know you've got some input into the whole development of this technology and its application to clinical assessment. How would you round his mosaic into kind of pointed language as to where clinicians should be going?
Yeah, so I think where clinicians should be going, if you want to see the big picture, I think is this concept that we understand that there's a lot of things that we are going to be able to and we do with the epigenome, and I think that the Omic age is a perfect example of sort of showing the potential of what we can do. We've shown this potential now in terms of one biomarker that's characterizing age, but then not only is it characterizing an overall measure of age in Omic age, we can then now disintegrate that down to each individual person and capture particular areas or mechanisms that they are aging in, right? That seem to be different. Even if someone has the same biological age, the mechanisms by which one person may have more acceleration in age versus another could be quite different. And that sort of gets at this concept Ryan was talking about, in that, these could be capturing sort of pre-phenotype, biologic changes that could lead to something very bad, but at a point where maybe they can prevent it. So I think that, looking at the epigenome now and what we can do with integrating that with other omic data to really further inform clinical measures for prevention is going to be an area that will continue to explode. And we're just at the beginning of it. And I think that this is going to be something that we are going to be able to tailor to diseases and disease subtypes. And that with more integrative multi-omic research that can be synthesized down into just one measure of DNA methylation, I think there's a lot of really transformative changes we're going to see in how we think about disease and how we prevent it.
So people have often asked me the question when genetic testing was just starting, should I have my genes tested? Because, maybe I won't be able to get much mileage out of that test presently because we don't know that much about how to interpret it. And my thought was, when it came down to a $100 test, the value proposition of that was more than worthwhile, and people should put their stake in the ground. Now I'm being asked the question about epigenetic testing. Is it too early? Should we wait? My answer to that is, when you see the rate of change of information that surrounds the value of this test that occurs on a weekly basis based upon the extraordinary amount of both clinical and basic science research that's ongoing around methylation age, I think everyone should start with this test. They should start with it first themselves and understand what they can learn. And then from that, it becomes a really marker tool for the reasons you're talking about for their patients. So I think this is not just a passing fancy. I think this is a deep new landscape of how we actually interrogate and understand much earlier upstream events that lead to downstream modifiable effects through personalized lifestyle intervention. So would either of you like to take a contrarian position to my advocacy?
I would say certainly not. So go ahead, Jessica. My apologies.
Yeah, I was going to say, I'm certainly not going to take a contrary position because I'm 100% an advocate of what you just said. I think that's a no-brainer thing that we need to be doing. What I would say, though, is, and I'd say this the same with the genome as I would the epigenome. If you just get your epigenome measured by yourself, you're not going to be able to take much out of that, right? Because if there's no information going along with it, you don't know how to interpret it. And I think that's been like traditionally a challenge with genetics, right? Initially we are all having our genome sequenced, but if there wasn't really a lot an individual could take out of it. They're just given the data. I think that's where we now really need to be thinking about utilizing the epigenome in conjunction with algorithms that can measure things like the biological age and can give you all these synthesized values that are specific to you that you wouldn't otherwise be able to get if you just had the epigenome returned to you without any interpretation.
And to add to that, I also think that one of the great things that we have tried to do, I should say, and the field has really been cognizant of, is using very similar infrastructure for a lot of the research. So whenever we do a test for any individual or patient at True Diagnostic, we're doing it on the same infrastructure to gather the same amount of data that most researchers in the field are using. So we're measuring, methylation at right around 950,000 locations now. And the good news about this is new tools come out to interrogate or interpret that data. Really, all we have to do is do data analysis. We don't have to get a new sample. We don't have to do anything other than run a new algorithm on the data we've collected. And so that's why we also try and do as much scale as possible. Some of these algorithms, for instance, in the case of even this new Omic age algorithm, uses approximately 1,000 CpGs, but we're measuring 900,000. And so the reason for that is because we might find something in 2 months that is clinically very, very important and would want to be able to offer that. And so we can actually do that. So in our next upgrade, when we're actually putting out all these Omic age reports, we're going to be adding reports for IL-6, C-reactive protein, fitness age, where we're doing grip strength, we're doing walking speed predictions, VO2 max and FEV1. And all of that is being offered free of charge to anyone who's done our test before. And so the good news is that as new things come out, we're actually going to be able to analyze that data and still provide value. And so I think that there are two ways to look at it. One is, what are you getting at the moment? The other is, what data are you getting, which can be interrogated in the future? And I think both of the answers are, I think it's still valuable, but certainly will only continue to be more valuable in the future.
On behalf of the Personalized Lifestyle Medicine Institute, I want to thank you both for an extraordinary gift of information that really, I think, shows where this technology can take us and the value proposition that it delivers today, particularly with the appropriate interpretation that accompanies it. I think True Diagnostics, that's been a co-sponsor and executive partner of us, is doing a fantastic job in pioneering this technology and helping to raise the bar for all of us in understanding the clinical importance of epigenomics. And I want to thank the two of you as leaders in the field for your skill in communicating what I know is a very kind of technically complicated and sophisticated topic into language that I think can really be translated into news to use. So on behalf of PLMI, thank you both. And for those of you that have had the benefit of of listening to this. I hope you'll share it with your colleagues. This is one of those front-edge technologies that everybody needs to be familiar with, and you need to start doing. That's how you become familiar with it and become a master of your own identity. Thank you both for your contributions.
Thanks.
Thanks. Yeah, thanks.